Good morning, and thank you again for coming. So what I'm going to talk about right now is a couple of topics. First, I'm going to introduce you to my favorite cell in the world. This is a CD8 T cell. This is what my laboratory studies. These are the cells that are probably most important, actually certainly most important in cancer immunology. I'm going to talk to you about some ways to make these T cells within tumors get activated. And I'm going to talk to you about some more technologies to activate these T cells outside of the body and then put them back in order to kill tumor cells. Finally, at the end, I'll talk about two very relevant and timely topics. One is the idea of giving two immunotherapies together. We're fortunate to have Dr. Wolchuk here. He's a pioneer in this in melanoma, and we'll talk about how it works. We'll talk a little bit about the side effects too. And then finally, I'll talk to you about a topic called biomarkers. That is, how can we choose the right patients for the right drugs? And then also, how can we make progress? How can we go forward in this field to design new and better therapies? So this beautiful orange cell on your left is a T cell. T cells circulate in your blood. When they're activated, they can go anywhere in your body. They can go into the brain. They can actually go into the bone marrow. What these T cells were designed or evolved to do is to kill infected cells. They have multiple ways to do this. A simple way is they just poke holes in it. But a more interesting way is what they do is they send signals to the target cell to tell it to commit suicide. They're the death whisperer. So basically those little blebs, those are called apoptotic blebs. This T cell has told this tumor cell to give it up. It's over. Commit suicide. It's interesting. T cells can kill cells that chemotherapy cannot kill, actually. There's really no cell that seems to be totally resistant to T cell killing with a few small sections. So these are cells. We love these cells. And it turns out if you look at tumors, lots of tumors have T cells in them. This is a clear cell kidney cancer. You can tell because the cancer cells are clear, right? And these brown markings are markings of T cells. So this is a tumor that's filled with T cells. And the reason we have this biopsy on this patient is not because the tumor is shrinking, it's because it's growing. So this is a patient with kidney cancer's original biopsy, and it's full with T cells, but the T cells are not killing. And the major advances in the field of immunotherapy have come about from understanding why they're not killing. And this is kind of why. So we're going to take a little time on this slide, walk you through it, and show you a couple of different ways. So this is a CD8 T cell. It's come into the tumor. When T cells are so powerful, right? I mean, they can kill anything. So your body designed ways to turn them off. One of the ways they turn off is by building this molecule called PD-1. And whenever a T cell gets into a tissue or into a tumor, it puts on PD-1 so that it can be turned off, right? It can be turned off. Tumors have figured this out, and they learn to express the foot that goes on the brake. That's called PD-L1. So what happens is a T cell comes into the tumor feels like it's under attack, and it expresses PD-L1. So the T cell's in there, it's trying to kill, but it can't because there's PD-1, and that's a sort of a quasi-stable interaction. We call these T cells in tumors that are not killing exhausted. So they're there. What's interesting is they don't just die. They kind of sit there, like I just showed you in the last picture. So there's tumors that are full of T cells. T cells have PD-1, and they're being turned off. So can you do anything about this? And the answer is yes. That's a little bit why we're here. It turns out that if you block the interaction between the brake and the foot on the brake, between PD-1 and PD-L1, with drugs, usually they're called antibodies, then you can get the T cell to restore its function. It can come back to life, actually. And if you're lucky, and in certain patients, these T cells can kill the tumor cells, leading to tumor shrinkage and occasionally really nice responses. Another way to think about that is not so complicated. In many tumors, these exhausted cells, if you block that exhaustion with PD-1 or PD-L1, their function is restored. And we know this happens, actually. We have data in patients, real live data showing that this happens. And I'll show you some of those data, not a lot, just a little bit. These are patients with kidney cancer treated with anti-PD-1. The way this graph works is each line is a person. These are real live people. These are patients treated on a clinical trial. On the first clinical trials of anti-PD-1, these are the kidney cancer patients. We start out with your basis tumor as a 0. That doesn't mean there's no tumor. That means that's what it starts as 0. If it goes up, that means the tumor grows. if your line goes down, that means the tumor shrinks. That's how these graphs are made. These are individual patients, tumors being treated with immunotherapy in clinical trials. And you can see from this image that not everybody, these drugs don't work for everybody. And I think it's important for us to be realistic and to understand the challenges go forward. In some patients, you give them these drugs, you block the PD-1 or PD-L1, and the tumor just keeps growing. That's unfortunate, but that's how it doesn't work in everyone. Some patients, though, are reasonably fortunate in that the T cells are poised to kill them. When you block PD-1 or PD-L1, those tumors shrink, and they shrink quick, actually, and that's what we won't want to happen to everyone. What's interesting, too, is many patients have neither of those. Many patients have their tumors go into this long-term stable state. And you might think, like, that's not a good thing, but you'd be wrong, actually. Data show that patients who develop long-term stable disease do amazingly well. They do almost as well as if their tumor had shrunk. So long-term stable disease, at least in kidney and bladder cancer, is a very good thing, actually. What's also amazing about this graph, and this is one of the things that the field doesn't understand, is this was a trial when we stopped treating after about 2 years. So these are patients who stopped getting immunotherapy, and their cancers didn't grow anymore, actually. This is a property of the immune system called memory. And you're probably familiar with this. That's why you get a vaccine, right? You get a vaccine to make immune memory so that when you encounter that antigen or that target again, your immune system remembers it, and it fights it stronger and better, actually. So we think that some of these patients might have immunological memory. That is, their tumor remembers, their immune system remembers the tumor. And just to point out that this is not just lines on a graph, these are real-life patients. This is a patient of mine. This is a patient in 2002, a very, very long time ago, had primary surgery to take out a kidney tumor. He only had cancer in his kidney, so the idea is if you do that, that can cure some of the patients. Unfortunately for him, it didn't cure his kidney cancer. It came back about 2 years later with multiple lesions, and he was treated on several clinical trials. When he saw me in 2007, early 2008, he had multiple metastatic lesions. Easy to see on CT scan, not so great for the patient in the lungs, even in the bones and also in the muscles in the back. I'll show you a picture of that. Brian will later on tell you about clinical trials. This patient enrolled in the first clinical trial of an anti-PD-1 immunotherapy, and he was actually the first kidney cancer patient ever treated with anti-PD-1 in this trial. When he started treatment, he had cancer every place in the body, but this is a beautiful lesion, not for him, but it's easy to measure in the musculature of his back. 2 months after his original treatment that had shrunk, we actually did a biopsy. We couldn't find any tumor cells, and by July of that year, he had no viable tumor. This was an early trial. At this point, we were very nervous that immunotherapy would cause adverse effects, autoimmunity, and so we stopped treatment, actually. And he went on to develop a complete response. He was last seen in early this year, actually. He's been off treatment now and tumor-free for about 9 years. He didn't have a lot of adverse events, and they've all since resolved. I need to emphasize very clearly that this is not everyone. Okay? This is not everyone. This is a small fraction of patients, but we do want it to be everyone, and that's the purpose of a lot of the research that you'll hear about later on, actually. This is the patients who develop immunologic memory. Some of these patients are still doing alive and well off treatment many years later. So again, the idea that the immune system can remember. Chemotherapy doesn't remember. Okay, so chemotherapy doesn't remember. So this is a difference between immunotherapy and chemotherapy. Are there any other ways besides blocking those checkpoints to help the immune system recognize and kill cancer cells? One way is if you look at this tumor, there are a lot of immune cells, but they're not working, right? So maybe you could do something to these immune cells, not in the body, but maybe out of the body to help them come back to life and regain the ability to kill tumor cells. This is an approach called adoptive Tcell therapy. This is used occasionally in melanoma, kidney cancer, other tumor types. The idea is that you take the tumor, you chop it up, frankly, you chop it up, and you isolate the immune cells, and then you grow them up over time, typically 2 to 6 weeks or so, until they're really activated, really very functional, and then what you do is you put them back into the patient. This is done again for melanoma at the NIH. It's called adoptive T-cell therapy. It's really fairly nonspecific. You just grow up many of the immune cells and then put them back in. There's a more advanced approach. Probably you've heard of it, and we'll ask Dr. Dievenbach to tell us a little bit about it later on, but it's called chimeric antigen receptor. So when you look at those T cells in the tumor, some of them are specific for the tumor, Some of them are not specific for the tumor. Some of them are really beautiful cells. They're high affinity, ready to kill. Some of them are weak, not so high affinity. Can you take T cells and make them better? Not just more of them that make them better. So the idea here is to reprogram that T cell so that it can specifically recognize a tumor target with high affinity. This approach is called chimeric antigen receptor. You replace the T cell receptor with this really simple high affinity triggering molecule so that these T cells can kill tumors. This was recently approved for some hematologic malignancies, some blood cancers. This is a patient in the New York Times treated with chimeric antigen T cells who actually looks like she's probably been cured of her hematologic or her blood cancer at this point. So those are two ways to try to make the T cells in the tumor better, stronger, faster by taking them out of the body. Some tumors, and I specifically showed you this, some tumors are beautifully full of immune cells and some are not actually. If there are not a lot of immune cells in the tumor, we're in a little tiny bit of trouble, right? There's nothing for PD-1 or PD-L1 to block. We can't take these cells out and make them better, stronger, faster. So there's other approaches to try to bring immune cells into tumors. One way that we sometimes talk about this, and you'll hear probably on the panel, is these are hot tumors, right? They're full of immune cells, and these are colder tumors. So is there anything that we can do to make a colder tumor hotter so that the immune system can have a better chance of attacking or killing the tumor cells? And there is, actually. I just showed you, when I showed you the picture of the tumor and the immune cells, I made it kind of simple, right? There's a tumor, there's an immune cell. It turns out that that tumor is full of lots of different cells. There's another kind of cell in there that's a bad immune cell. It's an evil regulatory T cell. These cells turn off our friendly CD8 cells. These cells express on them a molecule called CTLA4. So what if you gave two kinds of immunotherapy? Right? What if you gave anti-PD-1 or PD-L1 to get these CD8s activated, to take your foot off the brakes? And what if you did something about these evil regulatory T cells with another drug? And there is, in fact, such a drug. There's a drug that targets CTLA4 and maybe eliminates that regulatory function. Dr. Wilczuk is a pioneer in this field. What I can tell you, though, first of all, you can imagine if you do these two things to activate the immune system might get a little bit more out of hand, might get a little bit more overactive, and you might see more immune-related adverse events. And in fact, that's what happens. So if you give these two immune drugs, you see more inflammation in the gut. We call that colitis, more rashes, more inflammation in the joints. All those things become reasonably common. But on the plus side, what happens is most of the patients have a response, actually. This is a critical paper published in the New England Journal of Medicine. These are melanoma patients treated with the combination of anti-PD-1 or anti-CTLA4 combination immunotherapy. And you can see that most of these patients have their tumor shrink and shrink quick. So this is a good thing, and this is now a standard of care for melanoma and for kidney cancer as well. That's a combination immunotherapy. And that's where the field is going, actually, and that's a lot of the research that Dr. Tormi was talking about, actually, is what are the best combination immunotherapies. But what is the best combination immunotherapy? Probably not the same for everyone, right? So different patients have different things happening in their tumors. And as I told you, maybe not everybody needs combination immunotherapy. So there's a concept called a biomarker. What a biomarker usually means to us is we're trying to take a look at the tumor and try to predict what kind of therapy that patient might or might not need. Another word for this is predictive biomarkers. And I'll show you a quick example of that. So say we take a patient and we biopsy their tumor, and it's full of T cells, and it's full of PD-1 or PD-L1, then we can maybe just give anti-PD-1 alone. Maybe that's all that person needs. We can spare them the side effects of combination treatment, maybe have a nice response. Maybe we look in the tumor and there's another molecule. Maybe there's a molecule, I'll give you a name, LAG3. So maybe those patients need to have anti-PD-1 plus anti-LAG3. Maybe they need a combination, and maybe that's the combination they need, all right? Some patients, maybe they have cold tumors. Maybe they need a vaccine, or they need a different kind of combination. So that's the idea of predictive biomarkers. And this is a thing, okay? So for both bladder cancer and for lung cancer, for first-line treatment, we generally only give these drugs to patients who look like they're going to work in. So we look in the tumor and we see if there's PD-L1, we see if there's T cells, And if there's PD-L1 and T cells, then those are the patients that should probably get first-line immunotherapy for kidney cancer, excuse me, for bladder cancer and for lung cancer. So PD-L1 expression, you might hear this. Somebody with lung cancer gets their tumor tested. It's PD-L1 positive. That's a good thing. They go on an anti-PD-1 drug, and maybe the tumor shrinks, actually. So it's a pretty good biomarker. But I told you before, we don't know all the biomarkers. A lot of things that we don't know. So how are we going to figure this out? So Brian will talk later about clinical trials, but most of our clinical trials now include the idea that we got to get a biopsy of the tumor. It's not just for fun. Okay? The biopsy of the tumor is so that we can try to figure out new biomarkers and try to understand who responds to the drug and who doesn't respond to the drug. I particularly pick lung cancer because this is not just for clinical trials. This is for standard of care. If your lung cancer does not express PD-L1, you're not supposed to get treated with these kinds of drugs. And so that's why we do biopsies. So where is the field going? It's kind of complicated. There are multiple molecules on those T cells that probably are turning them off. Interestingly enough, they also have gas pedals. So the T cells also have molecules on them that you could push to make the T cells go faster, to kill better, stronger. And that's some of these molecules over here. That microenvironment I talked about, and I made it even a little bit more complicated, but basically we showed that there's in that microenvironment, there's lots of other things. You don't have to memorize these names or write them down, but there's a lot of other things that turn off the immune system that are being tested in the clinical trials that Brian will talk about later. But it's a promising time, as Jill said. I mean, we have good responses to either PD-1 based therapy or combination therapy in many tumor types and trying to move the field forward.